Hello. Are you able to listen to me? Am I audible to you? Are you able to see my screen? Okay. So this is lecture number 6. Today we will try to solve the assignment 1 and 2. And in the next class we will solve assignment 3 and assignment 4 and so on and so forth. So this is the example. This is the question which I have said that I will solve in the coming class. So the question is the combinations which have a group and its subgroup is an or R. So try to solve it, Patlika and Shivam. So the first question is, did you understand the question? Okay, no sir. So the question is saying that any group, let's say there is a octahedral in C4V. So this is a group which have other subgroups. So the combination of subgroup and the group is present in is present or not. So what are the options are correct? So the question is asking like that, if the group is octahedral for option A, so C3V is present in the octahedral or not, or in octahedral C4V is present or not, in C4V C3V is there or not, C4V C2V is there or not. It is like the group, the subgroup is the part of the group. So now I think it will be clear to you. A, B, D. Nice, nice. It is ABD. The answer of 4 is yes, ABD. Correct. So this is two links are here. I wanted to show you, but you have solved the question, so it is fine. Anyway, I'll show it to you in the coming class. I mean, in the mm, next question or next to next in this. So for this you have, so right answer is octahedral. This, sorry, not this one. This and this. Answer is A, B, and D. Okay. So in this, try to find out Okay, do not try to find out. I'll show it to you using this link. So let me just switch my share screen. So are you guys able to see my screen? Why am I? Because I'm presenting, I'm not able to see my screen here. Anyway, so oh, okay. So the question was, so are you guys able to see my screen? Okay. So so let's say for first example, which was tetrahedral. Okay, tetrahedron. So let's see how does it look like. Symmetry elements and see. This is your tetrahedron. This is your tetrahedron. This is your. So from here there is a C3 axis is passing. That C3 axis is passing from this and in the middle of the triangle. So how many C3 axes are you able to see? So basically all the three, like all the faces of this tetrahedron will have the C3 will have the C3 axis which will be passing through it. So this tetrahedron is having four faces. So total three C3 axes, four C3 axes are present. Uh, okay, like okay, this is understood. Anyway, this C3 is 8 is written because the C3 is C3 1, 4 C32 C33 means identity, one identity element. So if you like, all of them are giving the same orientation of the tetrahedron, that is why they have all the symmetry operations, total symmetry operations. E and 8 C3 is present here. And now look at the C2. How, if we are able to imagine C2, it is passing in the middle, passing from the middle of this edge and middle of this edge. So C2 is like that. Now the C3, in the C3 was passing through the center of the face. Now this is in the middle of the edge. So now you can simply look at that, how many C2 axes are present. So look at here, like you can simply imagine that 3 C2 axes are present here, because here, okay, someone wants to join. Okay, so turn off your mic. Okay, so if you look closely, that three sides are present here: one side, second side, and third side. So three axes will, three C2 axes will be present, which will be passing from the middle of this edge, middle of this edge, middle of this edge, and this edge will be have, and the one axis will be passing from the middle of this edge and this edge, like here. So you can see here. So three C2 axes are present. Okay. So this is the exercise I am telling you, because you already know it is tetrahedron. So let's look how it looks, the symmetry elements and operations are present in, like with it will be easier for you to visualize. Anyway, so this is the S4. In this, the animation is not here, I guess. Okay, anyway, I will try to show it to you. So this is your, let's say, tetrahedral simplest molecule, methane. See how does it look like, if you able to imagine. See, so S4, let's, so what is S4 requires? Let's say this is your S. See, okay, now I'm playing the animation. See, this is, and this. So let's say, what is this? This is the rotation, this is the reflection. Now first the rotation is happening. See, this is rotation. Now the reflection. So how this? So this is how the S4 is present here. Okay. Now try to visualize the planes passing through the tetrahedron. See, this is the plane containing this edge and passing through the middle of the backside edge. So it will bisect or it is bisecting your tetrahedron in two parts. So this is how this plane looks like. So you can imagine how, and also this is not your sigma h plane because C3 is present. So this is containing C3. So this could be sigma v or sigma d, but these are two C2 axes with these these two are C2 axes. So this plane is bisecting the angle between these C2 axes. So it will be your sigma d. So this is how you will try to find out that 6 sigma d's are present. I mean 6 planes are present which you can imagine here. Okay. So next, octahedral you have given the correct answer, but still I will show you the symmetry elements and other. So okay, so see, this is SF4. This will look like octahedron. This is your cubic n, Qn. This will look like a box. So let's take this one. Here is animation is present. Look how the C4 is present here. See, are you able to see? By rotating, by 90 degree. See, C4 is present. So here C2 is also present because C2 is the subgroup of C4 because here you are rotating this octahedral by 90 degree. This time you can rotate it by 180 degree. So C2 is also present. Now number of C2s, number of C4, you can figure it out easily now. So it is actually easier to find out. So anyways, now look at the C3. This is the C3 passing in the middle of this phase and this phase, the back phase. So this is your C3. I mean it is difficult to visualize, but animation is making your life easy. So that is how I can see that 4 C3s will be present here because this has 4 faces above, 4 faces below, so total 8 faces in this octahedral, and the one C3 is passing through 2 faces, so it is easier to calculate that 2 or 4 C3 elements are present. Obviously operations will be 8 because C31, C32, 4 will be there, so you can figure it out. Oh, and C3C is identity element. So C2 is this. C2 is like this. You are flipping this octahedral by 180 degree. Look at the animation. Okay. So how many C2s will be there? If you closely look, this is passing in the middle of, from the middle of the edges. So if you, how many edges are there? 8 edges are there and it is 12 edges. So 12 edges total, in total, and the C2 axis is passing from 2 edges. So simply calculate that 6 C2 elements are present. Okay. this is how the plane looks like. See, here is also animation is present. See, this is your plane. So if it will reflect this part to other side and vice versa. So how many planes you are able to see? 1, 2, and the 3. This one. I think it is easier to visualize. So three sigma v's I can see. Anyway, okay, sigma h. Okay, sigma is because okay C4 was there. That is why C. Okay, anyway, so because this octahedral is higher order of symmetry molecule or group, so there are lot of planes and axes are present. So here this the plane which is not perpendicular to your principal axis of rotation. So these are your sigma d planes. These these are your, because it is bisecting your C2 axis angle in two parts, like in equal parts. So and also it is bisecting the octahedron in two parts. So how many? So this is your one angle, like I mean one plane, one sigma d. So simply you can find out that how many sigma d's are present in this case. So these are the sigma d's present here. I think you are able to imagine. Okay, so 6 sigma d's are present here. Okay, now coming to the inversion center. See, in the previous class, in my initial class, I have also told you that how to find the point group of the molecule. So there was a systematic step-by-step procedure was there. I have told you. So procedure was find the AOS, POS, I, then S4, or something like that. So here they have also mentioned like that only. See, for octahedral, they have first tried to find out the axis of rotation. See, axis of rotation, C4, C3, C2. Then they have tried to find out the AOS, plane of symmetry. See, sigma S, sigma D. Now, third one, they have tried to find out the I, inversion center. Of course, this is the inversion center. This is the inversion center. You can just simply rotate. I mean, visualize. I is present here. Okay. Now, fourth, I've told you that in the procedure that fourth one is try to find the improper axis of rotation. So here, let's see. This is how it looks like. The animation is there. If you are able to visualize or not, I will have see. This is the animation. So this is your rotation. Rotation. Now the reflection. Now the reflection. So I think you are able to visualize it. Or I can so here also. What was the point of octahedral S6? S6. Anyway, it will be in the octahedral. So octahedron. See. So which one we are looking at? 6 S6. Okay. S6. Oh, lot of axes are. See. Now I am playing the animation. This is the rotation. This is the reflection. Okay. Now, so this was S6 improper axis of rotation. This is S4 improper axis of rotation is also there. Of course, this is simple to find out because you can rotate it by C4 just like C4 and the plane is obviously present here perpendicular to your C4. Yes or no? So improper axis of rotation S4 is present also. So how many S4s are you able to see? I can see that 3, right? 1, 2 and 3. Obviously these operations will be there. So this is how in total it will all the overall symmetry element of this octahedral point group are looks like this. So this is your octahedral example of octahedral. So proper rotation in a V6 P8 O24 polyoxymethylate cluster core. Okay, tetrahedral sonio. So what was the question? Tetrahedral is done of cubic and octahedron is also as from dodecahedron and icosahedron. Okay. Oh, icosahedron. Okay. This so this is the structure of this is the icosahedron. I think you are able to see, right? Okay. So dodecahedron look like this. Icosahedron and dodecahedron. So this they both of them are look quite similar to each other. If you look closely, they are actually similar to each other because pentagon. I mean the C5 axis is present here. See how this is look like here. This is your C5 axis here, here in the middle. One, two, three. This is the pentagon, right? Here also 1, 2, 3, 4, 5 pentagon. So C5 is present. See, C5 is present here. Now, of course, it is difficult to imagine by 2D that how many C5 axes are present. So let's try to find out here if it is there or not. Of course, it is there. Oh, nice. See, okay, not this one. Icosahedron, dodecahedron. What is the example here? Icosahedron. Okay, nice. Icosahedron. See, it actually looks like this. You have must seen in disco or bar somewhere this type of geometry in the disco ball, which is there. So it is highly symmetric in nature if you can visualize and look at it. I think so. I can, yeah, this is the best side you can look at Here is everything is present. You can just so see how many axes and how this is rotated. So I can show you that this is how many C5 axes are present. See, just for the visualization, look at it closely. So how many six C5 operations are 24? Okay. Now in this also you will find out C3 axes are present here. So C3 axis, obviously here it is difficult to imagine, but look how this looks like. This is a nice website to actually visualize. See, obviously I can show you the animation also. See, in those mostly the C3 axis passes between the faces and rotate the whole structure to its equivalent structure. Okay, C2 is present. Obviously, it is highly symmetric, so C2 is always there. C2. See how many C2s are there. Look closely. Isn't it looking very nice? Highly symmetric. Okay, so planes. Obviously, planes you can imagine easily. Planes are present here. Planes I can show reflections. Oh, so many reflections. Oh, 15, huh? 15. So this is the problem with the higher order symmetry molecule or the structure. Okay, nice. See, this is the one plane. This is how it reflects the one side to other. See? Okay. So total 15 sigma, 15 planes are present here. Now, find out the I. Obviously, it is I. Okay, try to see here also. I. I am not able to see I here. Okay, here this is I. Inversion center. So, are you able to understand that why this animation is like that for inversion? It is because inversion is like this side of the structure will interchange with this this side. That is why the animation is like that. See, everything is going in the point and then again reflecting back to it, the original structure. That is why the animation is like that. Anyway, moving on to this S10, you can easily imagine just animation is also here. See, this is the rotation, then the reflection. So 6 S10 is present here. These are the cyclic molecules. Anyway, okay. So I think what I wanted to show, this is the determination of the point group. What I wanted to show, I have shown you anyways using those two links. Now coming back to our question and answer. So my screen is visible to you. Shivam is saying yes. Okay, nice. This is done. So tetrahedral, octahedral. So point group of these two was IH. Nice. Mm, okay, not later. This can be done. Okay, for a group with H equal to 6, a subgroup with H equal to 3. What do you think, Patlekha and Shivam? What will be the answer? Is it too small to see, or I can make it visible to you guys? Okay. Okay. So, what is the answer? Tell me. What is H, sir? Okay. So, looks like you are not watching the videos. Anyway, moving on. Try to solve this. For an octahedron, number of C3 accesses is. Number of C3 accesses is 8. C3 accesses, not operations. Octahedron. Like this. leave it. I'm making it worse. Hey, look at this, no? This, and then try to visualize how many C3 accesses are present. Like this, right? Now try to tell me. I think you are not able to see my previous screen where I was showing you octahedral. I'm scrolling it down. What was the question? C3 accesses. See, how many C3 accesses are you able to see? 4 C3 accesses. Is it okay? Yes, now? I'm not able to see your messages, so I don't know. Shivam is saying 4, Patlika is saying okay. So I'm assuming it is okay. So 4. Okay, coming to this one. Try to find out Patlika and Shivam. Point group of course it is difficult to visualize, but these types of questions will come in the exam and also you have to solve it. Or you can do one thing, try to eliminate the answers. So let me draw the structure first for your all the CO molecule. So CO is connected to each one of the CO. So it is like CO because this, let's say consider this CO is connected to all three. This CO, it is connected to all three. So it is like this CO is connected to all three, and all the COs are connected to each of the COs. Cobalt. This is your CP ring. Like this. Okay. Now try to find out quick. I think I have given you enough hint. So okay, Shivam is saying S4. Are you able to visualize this S4 or just you know the answer so you are saying S4? How you are saying S4? Tell me. it has C4. Nice. C4 is there. Okay. So C4 is there. This option is not the possibility. This is not the possibility. Only this and this is left. Okay. Now next you are saying S4. So why not this one? Because principal axis of rotation here is also C4. C2 I cannot find. No, you cannot find. It doesn't mean it will change the point group of the molecule. First tell me why are why are you saying like this? See, if C4 is present in the previous example I showed you, C4 means you are rotating it by 90 degrees for 4 times to reach the identical structure, which means C2 will be there. You rotate it by 2 times only, by 180 degrees. C2 will be there. Why not? Okay, you are saying if C2 is not there, then it cannot be D. No, C2 is there. C2 is there, no? So for DH, D4H, H is telling you that there is sigma, plane is present. If you try to find the plane, because this is above the plane, this this portion of the CP ring. So if C4 is like this, this sigma H will fill up your CP ring. This will go like now at present this portion is above the plane. If sigma is there, if you reflect the molecule, it will fill up your molecule, the CP ring. So this portion will go below the molecule, below the plane. So that is why sigma H is not present. And also C2 is present, but maybe not perpendicular to CH. That is why this option is not correct. Am I clear? Or okay, okay. So this example I can show you in the submit the website, this website also. Exact example I was searching for yesterday. I was searching for, so yesterday I got the same structure in this website. See, look like so the cobalt 4 CP4 cluster looks like this. See, let's see. You are saying C2 is not present. Let's see. C2, see C2 is present. See, how does it look like? Let's see. It is, see, it is going, passing in the middle of the molecule like this. So C2 is present. Okay. Anyways, Shivam, it is okay to you. Okay. So, next question. Conversion of boron trifluoride to tetrafluoroborate accompanies. So, question is saying BF3 is converting into BF4 minus. BF3 looks like, okay, no, you tell me, you try to solve it. What is the point group of BF3? D3H. Nice. Okay, now of BF4, point group of BF4. Tetrahedral. Nice. This is tetrahedral. TD. Yes. Okay. Now this atom is boron. So boron is, the orbital diagram is 1s2, 2s2, 2p1, right? Hydrogen, helium, lithium, beryllium, boron, 5. Yes, it is correct. So, okay, after the hybridization, how this will look like? So, 3 fluorine. This is of beryllium, this is of fluorine. So, 3 fluorine will make the bond. Okay, fluorine. Now, so this orbital is vacant, right? 2pz, or let's say 2pz. Okay, so this is vacant. Here this fluorine molecule is having this lone pairs. So there is a chance of back bonding, because this is having extra electron and vacancy is there, vacant orbital is there. So back bonding is possible. If back bonding is possible, back bonding is happening, which means that the bond will be stronger and shorter. Bond will be stronger and shorter. Here, in tetrahedral case, what is happening? 4 fluorine is coming. So this vacant, is already filled by this fluorine. This fourth fluorine. Fourth, not like this. I should have used the other. Okay, this is your fluorine. This is your fluorine. So this fluorine will fill this electron, this orbital of the boron, right? So that is why chance of back bonding is not present here in this case. So now tell me, what is the correct answer? Now I have given you everything. like told you. So try to find out the answer. So here it's saying increase in symmetry, decrease in symmetry. So to find out the increase or decrease in symmetry, you can find out the order. So for D point group, it is n into 4. For C point group, it is n into 2. So for tetrahedral, this is your tetrahedral, right? So what will be the order? 3, 3 into 4, it is equal to 12. Okay, 12, 3, 3. This is for DS3. DS3. So order is 12 for DS3. And tetrahedral, it is higher order symmetry having 24 order. Order of tetrahedral is 24. So order is increased, right? Which means, what does it mean? It means symmetry is increased. So these two options have eliminated. Now tell me about the bond elongation or contraction. What is happening? Okay, okay. You have already given the answer. Okay, nice. Bond elongation is happening. Okay, nice. Now try to find out the answer. C2 number of C2 excesses in CCl4. First, try to find out the point group of or the structure of this CCl4. Of course, you know, but tell me. Of course, tetrahedral. Yes, it is tetrahedral. So in tetrahedral, tell me how many C2 excesses are present? 3. Okay, it is actually right. So are you able to visualize those 3 C2 excesses, or I can show you this structure of the I can show you the structure of tetrahedral and C2 excesses so you can visualize easily. Please, so okay. No, no, not methane. Okay, okay, nice. Okay, the consider this as CCl4, like I mean the Cl, and the middle atom is carbon. Okay, so C2 axis, you can imagine, right, like this. Which is like to this and like this. This is your tetrahedral. So is it fine? So three C2's axes are present. Okay, next question. Point group of these two. So first try to find out, like, by solve this question by eliminating the options. Then it will be easier to find the answer of this question. So here you can see that the principal axis of rotation is C2. So it's all the options having C2. Maximum axis of rotation is C2. So principal axis of rotation is C2. Just tell me, if there is C2 you are able to imagine, tell me you are able to find the sigma, any plane, any plane. If you are able to find any plane, then the answer will be different. If you are not able to find the plane, you can just simply find the answer of this question. Because if C2 is present, which means two C2 axes are perpendicular to each other, is not present. If they were present, the point group would be D2. So D2 is not there, which means two perpendicular C2 axes are not present. So it is easier to find the plane now. If you are able to find the plane, then the point group will be different. If there is no plane, then the answer would be something else. So for this molecule, are you able to see the any plane, sigma d, v, h, any plane? Okay, no plane, no plane. Both of you are saying no plane, no plane. Yes, there is no plane present. It is right. It is right. So, if that is the case, then your point group should be C2 for this one. So what will be the answer then? Simply, it looks very difficult initially when we have started, but I have given you some hint, right? So that hint is making your life easy to solve the question. Anyway, are you able to imagine this molecule? No. So imagine like in the middle, one m is here, one m is n is here, one n is towards me, one n is away from me, and so this is in the plane. So three atoms are in the plane, three atoms. Okay, this Cl and this N is above the plane. So M, N, and Cl is present, N is present, and and the below of this plane, here the N is present at this position, here N is present, here Cl is present. So it is like M away from me N, towards me N in the plane. Above the plane Cl is here, below the plane Cl is here. Above the plane N is here, below the plane N is here. I think it will be quite clear to you now. Yes. So these two are bidented. These two are these are bidented ligand. Okay. Then bidented ligand. Okay. Okay. Nice. Okay. We have solved this week 0. Solved week 1 assignment. We have solved. Okay. This is I will solve coming to we will see this example in the coming classes or maybe this class. Okay, coming to assignment 2, try to solve or tell me, do you know how to make this transformation matrix? Any idea? Okay, so let me, it is like, so the question is saying transformation matrix for clockwise rotation of unit vectors along x, y, z direction by angle theta with respect to y-axis is. So let's say this is your transformation matrix and this is your basis. So basis is like on which you are uh, doing this operation or transformation. Okay, so it is like any symmetry element. This transformation is happening of, this is like of the molecule of, let's say this is the representation of basically, okay, for any complex molecule or to, it is difficult to visualize, then it is always the possibility to do these operations by using your computer. So for using the computer to solve those kind of question or complex example of for complex molecules, we can convert this into the number form or in a matrix form, so your computer can do this. That is why this operation or this matrix is came into the picture. That so this is the like the transformation matrix, right? This is the transformation matrix of any molecular bond, okay, atom, or of the whole molecule, anything. Let's say we have seen one is A matrix is multiplied with by B. So after this transformation, you'll get the A dash, which is not equivalent to A1 unless and until this V is identity matrix. So what is identity matrix? It is like 1, 1, 1 and so on and so forth, 0, 0, like this, right? Let's consider this only 3 by 3. Oh, consider this 3 by 3 only. So if this is there, if B is I, identity matrix, then of course, if this is the case, then A will be equal to A dash. If this is not the case, then these two are not equal. So here B is like your basis. So what operations you are doing on your bond, atom, or the whole molecule. Okay. So let's. I think it will be easy. I can show you. Okay. I'm writing here now. It is like for rotation. For rotation matrix, it is like this n number. You know the rotation, the C2, Cn, or anything. So this number n is given by 360 divided by the theta angle at which you are rotating your molecule. So to transform, say this transformation matrix, so this is for Cn, right? Transformation matrix. So matrix representing symmetry element. Okay, like X, Y, and G. So this transformation matrix, this transformation matrix represents the symmetry elements. So let's say for identity, like 3 by 3. So this is I have already. Okay, this is identity. Why identity? Because let's say this is your X, Y, and Z. You will get A dash, Z dash, Y dash. This is 3 cross 3. This is 3 cross 1. This will be, so these two are same, right? These two are same. So what will be your new matrix? 3 by 1. This is we have learned in our BSc MSc. So and these were your coordinates, right? Original coordinates. Now it has changed to this. These are new coordinates. Okay. So this is your identity matrix. And so basically this is your basis. So what I wanted to say is that this is your basis, means that these were your coordinates at which you are doing the operation and getting the new coordinates for the getting the new coordinates. So these are your bases, which can be coordinates, bases which can be coordinates, or you can do this operation on orbital. We have one example of orbital. So orbital atoms, or along the atoms at which you can do this operation, bonds, anything, anything, anyway. So here, uh, okay. So in this example, in this example, in this example, in this example you are getting the same. So x1 is equal to x, y1 equal to y, z1 equal to, or not 1, this is z prime, x prime, y prime. So these are same because this was the identity matrix. So here we have observed no change in the basis. In the basis, these were our basis coordinates. Coordinates were our basis. So identity does not change your basis. Okay. Next, coming to reflection. First one was identity. Okay. Reflection. Reflection means plane or sigma, right? So it is like x, y, z, v, w. Okay. So this is I'm saying that it is planar molecule, right? Planar, hypothetical planar molecule. Now, and this is your x, y, and z. This is your axis coordinates. Now I'm saying use the plane yz. Yes, yz plane. So after operating this yz plane, so this will be your yz. This will be your yz. So y, w, and x, these will remain in this only, in the plane, yz plane. But v and z will exchange their or interchange their position. V, z, like this. So this is your plane. Okay. Which means that whatever is, I mean, the bond, molecule, I mean bond or atom or the whole molecule is present on particular plane, that will not going to change its position. So let's say I am saying for xy plane, xy plane, xy plane for the same, what will happen? X and y remain same, z becomes minus z. So what will be the transformation matrix? It will be 1, 1, minus 1 for 3 cross 3 transformation matrix. So this is transformation matrix of sigma x y. Similarly, you can write for other plane also. Let's say x z. So it will be like x. This will be your minus. This will be minus because y will change. Next, and of course 0, 0, 0, 0, 0. And for y and z, 1 will minus v. Then These will be same, right? Okay. Now, now, so let's say I have considering the same plane sigma x by. So what will be the transformation? 1, 1, minus 1, 0, 0, 0, 0, 0. Bases are coordinates. So what will be the new basis? You know how to do the multiplication, this how to solve this matrix. It is like 1 multiplied by x plus 0 multiplied by y plus 0 multiplied by z. This will be your x prime. Y prime 0 multiplied by x, 1 multiplied by y, 0 multiplied by z, y prime 0 multiplied by x, 0 multiplied by y, minus 1 multiplied by z. This will be your z prime. So just try to solve this. What will happen? This is 0. This term is also 0. It will be x only. This term is 0. This term is 0. Y only. This term is 0. This term is 0. This is minus z. So your new Cartesian will look like, how it will look like? It will look like x, y and minus z. So this is the plane. So these coordinates will not going to change its position. Z will be opposite direction. So that is why the minus sign is there. Can you take any bright color? Okay. There is one concept is also there, mixing of coordinates. So mixing of coordinates, mixing of coordinates will be there if why there is no other color. Okay. Okay. So mixing of this coordinates will be there. Oh, this is not visible or not good, not good. Mixing of coordinates. How, just say you have any transformation matrix, how you will figure it out? That is I will going to tell you. These zero terms, will not remain zero, which means that let's say you are considering the coordinates only, position. So the position will not be in the exact x direction, y direction or z direction. Maybe it is in between. Let's say x, y, and z. So this is the point. Let's say the length of this vector. Let's say this is vector. Length of this vector is L. This is theta. So L equal. So what will be the x here in this case? X will be x L cos theta. Y will be L sin theta. Okay. So for other two, I have okay. Other two I have solved, right? X, Y, Y. Okay, I have told you. Now coming to the third one, rotation by an angle theta. Okay, consider this example: C O X X, this is Z, this is Y. Okay, these are your coordinates X, Z and Y. Now I'm saying you rotate this molecule by x-axis, along the x-axis. C Cx. Okay, so what will happen? Let's say C2 is there, C2. So this is C2 C2x. What will happen? This will change this molecule. Y is there, Z will be here. Am I right? Okay. So here you can see atoms on this axis are not going to change their places. What will change? And the atoms which are present on other axes other than this axis will change their position. So in this case, Z and X, Z and Y, these two are changing its position. So now, why we are studying this? Because we want to find out the transformation matrix for all the operations, all the elements or operations. So now we have seen the transformation matrix for identity and for this plane reflection. Now this is the time to find the transformation matrix for rotation, like the C. So this is C2x. Try to find out what is changing, what is not changing. So only this is changing, not changing. Because along the x-axis, in that x-axis, in the x-axis, atoms are present. They are not going to change its position. Other atoms will going to change its position. So this will remain 1. These two will be -1, -1. So this is the transformation matrix for this C2x. Similarly for C2z, I think it is easier for you to now tell, right? Only this will remain constant, well, I mean same, and for mm, and for C2y it will be like 1, -1, 1 and -1, 0, 0, 0, 0, 0, 0. Okay, now so this time uh, here, not here, here we are uh, let's say taking the example here, here. So here it's like 360 divided by 180. So n is your 2, or you would say that you know that theta at which you are rotating the you are rotating your molecule, then you know that the position of the other atoms is changing, but I mean interchanging or changing their x is remaining same, and y is changing to z, and z is changing to y. But let's see, if you are rotating the same molecule, which I have drawn in here, x, x, c, what was that? O, O, Z, Y. Okay. Let's say now you are not uh, rotating by 180 degree. Let's say 60 degree, or I would say 62.5 degree. Then how this transformation matrix will look like? So there is a formula. Not formula, I mean the matrix. Cos theta 0 minus sin theta, cos theta minus sin theta 0, sin theta, cos theta 0, 0, 0, 1. Because this is z. Because this is z. So in this case, it will be like y, x, x, and z. The principal axis is z. We are rotating the molecule along the z direction. Okay. So this is like, this is, what is this? This is your transformation matrix for rotation by, this is for rotation, by angle theta, this theta, along z axis. Why z axis? Because this is remaining 1. Okay. Let's see what will happen if you try to operate or transform these coordinates from this transformation matrix. So it will be like x2, y2, z2. Now tell me how it will look like. It will be like x1 cos theta minus sin theta y plus 0 equal to x2, and sin theta x1 plus y1 cos theta plus 0, and 0 plus 0 plus z1. Okay, this is y2, this is z2. So the new transformation matrix, I mean the matrix, not the matrix, coordinate, maybe matrix, it is matrix of 3y1. So new coordinates will be like this. These are the new coordinates. These are the new coordinates. Okay. So these are the new coordinates. Now you can see that these two are not changing. These two are same, z1 and z2. But x1 and y1 have changed, and this x2 is a mix of x1 plus y1. This x2 is a mix of x1 plus y1. So these two are mixed coordinates. So this is the mixing of coordinates. Okay. Now try to find. Now we will try to find the. Let's say this is cy and y. So here y is fixed, right? This is because this is along the z axis. The same thing. This is z, this is x. So this point will be x1, z1. Now after and the Cartesian the coordinates will be x, z and y. So by this operating this cyn in clockwise. How it will look like? It will look like it will change its position to here. Why it will change its position? Because I am rotating it to by clockwise direction, like this. This is theta. This is theta, full theta. Okay. This is your alpha. This is theta minus alpha. Okay. The next coordinate, the new coordinate will be x2 and minus z2. This is minus z2. Okay. So what will happen then? And n is simply like how much angle you are giving, at which you are rotating. Then you can easily find out the n. Okay. So what will be the x1 here? It will be L, because okay, this is the length of this is L. Will be L cos theta? No, not all L cos theta. It will be L cos alpha, and y will be not y. This is z. Z will be L sin alpha. Okay. Now, what the new coordinates will be? X2 is equal to x2 will be L cos theta minus alpha, because this is theta minus alpha. This is full theta. Right? Yes. And you know already that cos theta minus alpha from the trigonometry, cos alpha sin theta sin alpha, and the next one is, here we have used this one only, right? Okay. So x2 will be L cos theta cos alpha L sin theta sin alpha. L cos alpha L sin alpha. This is x1 cos theta. This is z1 sin theta. x2. This is how you got your x2. Similar to this. X1, y1, cos theta minus plus. Here we were rotating along z direction. Here we were rotating along x y direction. Okay. The next is this minus z minus z2. So minus z2 will be like okay in the line, okay, it will be L sine theta minus alpha. Okay, so I would L sine, okay, I'm in L sine theta minus alpha, and you must be knowing this identity. Sine theta minus alpha will give you, can be expanded like sine theta cos alpha minus cos theta sin alpha, right? So Z2 will look like minus L sin theta cos alpha plus L cos theta sin alpha. Okay, this is your Z. This is your X. Okay, Z1 is L sin alpha. L sin alpha. This is your Z. Okay, these two, multiplication of these two is Z1. Okay, so it will look like, so Z2 will be Z1 cos theta minus this is X1 sin theta, because L cos alpha is x1 and y. So we know now this, no x2 we know new Cartesian, z2 we know new Cartesian coordinate, y1 is equal to y2 because we know that we are rotating along that direction only. Okay, so now I'm writing here x2 x1 cos theta x1 cos theta z1 sin theta z1 sin theta. Okay, in z2 y2. Okay, now try to write down the transformation coordinate, this matrix. So x1 y1 z1 x2 y2 z2. Now this is like I have done the, I have this rotated the molecule or change, this transformation has already been done. Now I am trying to find the transformation matrix. So we know that what is x2? What is x2? x2 is multiplication of x1 to cos theta. So the cos theta will come here. Now we are making the transformation matrix. Okay. Next, y term is not there, so it should be 0. Z term is here, so sin theta is here. Should be here. For y2, y2 is equal to y1, so this is 0, 1, 0, simply. Okay. Next, z z2 how is, okay, this is minus x1 sin theta, so this will be minus sin theta. No y term is here, so 0, this should be cos theta. So this is This is your transformation matrix for CYN. Okay. So this time we have what we have taken clockwise, right? In this direction, clockwise. For anti-clockwise, what will happen? This point. I should take this. This point will be here. It should be here. So the sign will change here. So this it should be specific. The transformation matrix is specific to the rotation. In which direction you are rotating your molecule. So okay. I think what was the question? Okay. So what was the question? Transformation matrix for clockwise rotation of unit vector along. So they were asking for transformation matrix for clockwise of unit vector xyz direction along xyz direction. So they have the bases are here as is this xyz direction or coordinates by angle theta with respect to y axis. Okay. This is we have solved only. So what was the answer we have got? Cos theta minus sin theta, cos theta. Ooh. Cos theta minus sin theta. Okay, I think this is the answer. Okay, this is the answer. So A is the answer. Okay, this was very long explanation to you guys. Are you guys here? Did you follow? I mean, this is very long explanation to tell, but it is important to tell. Yes, sir, got it. Okay, nice. Okay, nice. Now, this is the second question. Consider CO3 minus ion depicted. This is like they will be in 1, 2, 3, 4 in resonance. Okay. In the figure, the 3 oxygen atom are depicted as 1, 2, 3. So 1, 2, and 3. 1, 2, 1, 2, and 3. In the middle 4 is your carbon atom, and the C is designed as your 4. Okay. Question is saying taking PZ orbitals. So these are PZ orbitals, the 3 oxygen atoms as the basis. Okay, so they have represented these orbitals. These are PZ orbitals of oxygen 3. This is of 1 PZ. This is PZ of 2. So these are the bases now. And the transformation matrix is this. So now they have given the transformation matrix and basis also. Now they are trying to find out now they are asking, the question is asking that represent the symmetry operation. They are asking for the symmetry operation now. Simply means that which symmetry operation is present. So this you can solve only by looking at the transformation matrix, because by doing the operation as we have discussed just now, by doing the operation, what we see, what we make the transformation matrix along those bases. So now look at the transformation matrix, then you will get the operation, which operation is present. Okay, so what is not changed here? I think this 1, right? Because in diagonal 0 0 is there, 1 is off diagonal, this one is also off diagonal. So only diagonal element which is not changed, diagonal position is this Z, this Z. So now try to find out, now it is simple I think. Try to find out if which element symmetry operation or element is possible. So which symmetry operation is possible? Now this is a enough hint. Okay, Patslekha is saying C. How is C? Because the in the option is sigma h x y. The C option is sigma h x y, which means the Z will change. But in the transformation matrix, Z is remains the Z. I mean Z is not changing. So you should look for that operation in which the Z is present. I mean along the Z axis the operation is happening. So this option is eliminated, this option is eliminated. Which option is left? This one, C3 plus this XY, YZ plane. Okay, both of you are saying then D. Okay, so did you get it? How this? Okay, answer is correct. I know answer is correct. So this is just your guess. You guys are guessing it, or just you have solved it. Okay, explain me why not C3? Just just guess. This is not. You are giving answer, so I thought you know how to do it. So it's not the correct way to answer the question. No, it's simple. See, uh, see, two options already have eliminated. these two. Look for C3Z. So what will happen in if we do the C3Z operation? X is here, Y is this, Z is in this direction, and this, you know, this is a planar molecule. What will happen? Simply C, C, O, 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 but the for this is for, but the position will change. 1, 3, 2, because this will be your C3. This will be your C3Z. This will be your C3Z. This will be your C3Z. Like this is planar molecule. We are rotating by 120 angle. So the position of the O atom will change. So if you look closely, what is happening? PZ1, PZ2, PZ3. Basically, what is the new position of this oxygen is constructed? So position 3 has been occupied by 1. So this will be PZ1. P2 will occupied by PZ3, and this 1 is occupied by 2. Am I clear? Till now, Pat Lekha, because you were guessing. So yes, okay. Now after rotating, or doing the operation, C3Z operation, you know the position of your orbital of the oxygen molecule, of oxygen atom, and the new orbital position of the oxygen atom. Now try to find out the matrix, transformation matrix. So how it will look like? It will look like, so you want this 2, you want PZ2, so 1 is here. You want, then other two are 0. You want P3, so 1 is here. Other two are 0. You want 1, so 1 is here. Is it making sense? Yes. Because 0 multiplied by this, 1 multiplied by this, 0 multiplied by this, and summation of all three will give you PZ2. This. Similarly, multiply this, and this, PZ3. This multiplied with this, other two will be 0, PZ1. So a transformation matrix will look like this. For this, am I making it sense to you guys? Okay, so tell me, this C3Z transformation matrix is similar to this matrix? Not similar, same to this matrix? Yes or no? Answer. No, yes, it is not similar. See, 1, 1, this here no 1 is here. So this answer is not correct. By eliminating, you can just simply find out the right answer. Okay, we can try to find out the transformation for this also. Now we know. Now we know the answer is D. So let's do the operation and try to find out the Cartesian. I mean the new this basis. Okay, what will happen? 0, 1, 0, because you know the transformation matrix. 0, 1, 0, 1, 0, 0, 0, 1, 1. Basis you know. Or we can do other way around. So what is the sigma v yz, sigma v yz? So this is the plane. This is the plane. What is happening? Hmm. So what is happening? Yz, in yz plane. This is your yz plane. 4 carbon atom is present. This is present. This will this O orbital, or I would say the pz orbital of oxygen atom number 3 is present. So 4 atom 3 will not going to change its position, but the position of 2 and 1 will be interchanged. Okay, so the new position after this sigma v yz will, after this operation, it will be like CO O. This is a 3, this is 4, O, this is 1 now. This oxygen is 2. The new position will look like this of oxygen atoms. Oxygen atoms p orbital. Okay, now try to find out the transformation matrix. So what was the basis? What were the basis? PZ1, PZ2, PZ3. Now PZ3, PZ, PZ, PZ3, PZ3. This PZ3, PZ3, 3. This is not changing. This atom is not changing. So PZ3 new basis. So this is same. This will remain PZ3 only. What happened to PZ2? This position has been occupied by PZ1. So this will be PZ1. This position has been occupied by 2. PZ2. So this will be PZ2. Okay. Now you know the old basis, new basis. Try to see the transformation matrix. Try to see the transformation matrix. So if you want this to be transformed to 2, here should be 1. 2 has transformed to 1. So this should be 1. Others are 0. And this is not changing. So this will be your transformation matrix for C, V, Y, sigma V, Y, Z. Symmetry operation. Okay. Now try to, if this is correct, then this transformation matrix I have calculated should be similar to this transformation matrix. So these two are similar or not? Not similar, same. This should be same. Yes, it is same. They are same. So answer is D. Nice. So what is the time? 2 hours 7 minutes. Okay, I'm stopping my session now and meet you on the next Sunday 4 p.m. Bye. And in the next session we will solve assignment 2, 3, 4 and whatever we could. Okay, I'm ending the session. Okay, bye.